can go ahead and start now.
Okay, Ayo, go ahead and start the meeting. Ayo, we can't hear you.
Yeah, I can hear you. Check your audio.
I guess it's clear now.
Yeah, that's good.
Okay. All right. Good morning, everyone. On behalf of the Nigerian Association of Petroleum Explorationists, Abuja chapter, we welcome everyone here to the Jones technical meeting. And we would like to appreciate the national body for the opportunity granted us, the support we received as well from you. In the course of today's meeting, we'd like to quickly appreciate key personalities here. From those we can see here, I think we can see the president of NAPE. We can see the president of NAPE, Dr. Mrs. Patricia Otogu. You're much welcome, ma'am. Hello. Okay, you're much welcome, ma'am. Then we can see.
Thank you. I am not a doctor. Thank you. I'm not a doctor.
Okay. I'm giving you doctor ahead, ma. Okay. Then we can as well see members from the publicity units. Mrs. Tubos Rafulayo. We can see Mr. Tunde as well from the publicity. And we can as well in the attendees section, we can see Mr. Adelola Adeshida. We can see, okay, the attendees are still being populated, but prior to that, once we have key people coming in, we'll definitely recognize them. Without further ado, we proceed to the meeting proper for today, so that we have ample time for our guests for today. All right. I think I would like to hand over the control to the president, to the chapter coordinator, Mr. Ehi Bazwai, for the opening remarks before we then call the guest speaker. Mr. Ehi Bazwai, over to you, sir.
Thank you very much. I also would like to acknowledge the presence of the one-time president of NAPE, Ajubola Oyebamiji, FNAPE. Thank you very much. We want to say welcome to all of us to this technical meeting of the Abuja chapter. It promises to be an interesting one. We have the guest speaker who will be introducing any moment from now to give us the talk. And we want us to get our bios and our pads ready to take down some notes and also to ask as many questions as we can. It's going to be technical, purely technical. And we believe that we all leave this place with a lot of knowledge. So if you have questions, you have to ask, you can just drop them in the Q&A section. And then questions will be taken at the end of the presentation. So without much ado, we'll just move on. So I hand over to you again, Ayo, to continue. You're muted, Ayo. You're muted, Ayo.
Muted now, yeah, good. Okay. So, sorry, please. All right. Okay, so our speaker for today, he has a PhD in structural geology, in field-based fracture analysis of the Variscan orogeny. He has worked as a consultant at Barclays for 14 years in the role of project structural geologist, specializing in structural geology, seismic interpretation, fault seal analysis, and geomechanics. He has worked with super majors and independents in many hydrocarbon provinces globally, tackling issues faced by both exploration and production. Ladies and gentlemen, fellow NAPE members and guests, please help me make welcome of the virtual veteran, our speaker for today, Dr. Dave Quinn. Dr. Dave Quinn, over to you, sir.
Well, thanks very much for the introduction. Hopefully you guys can see me, hear me. I'm here in a very wet, dreary part of the UK. Yeah, excited to join you this morning. And thanks for the introduction. It's very kind of you. And we have worked with a lot of the big names that you'd know and some of the small ones that maybe you wouldn't in the industry and on a lot of different problems. But in the preamble this morning before you joined us, we were just kind of talking about what the talk was about, and your president Patricia offered a very interesting insight, which is, we get new seismic and we get new data, we get new technology, but the fundamentals don't go out of fashion. That it's the basics that we have to keep one eye on because we know they're the truths. And so that's hopefully what I'm kind of going to speak to you today, which is basically, what are the fundamentals of mapping and seismic interpretation that you could potentially, hopefully, if you find this of interest and of use today, take into your own jobs. Because look, a lot of us kind of sit and interpret seismic. A lot of us, certainly almost all of us, I would guess, are using a map from time to time, at least, and it's useful to know something in addition to what you can do with that map, because there's a few more tricks that you might be able to apply to them. And I'll briefly talk about fault seal analysis. It's not a fault seal analysis talk by any means. I just kind of that's our speciality, I guess. As a consultancy, we kind of specialize in fault seal analysis, and our software does too. So I just kind of drop it in as an aside, but it's more about seismic interpretation in general, really, because I would say the most important part of a fault seal analysis is the fault. The fault analysis part of the words fault seal analysis is definitely the most important work that you can do. So the presentation today will kind of have 4 sections to it. The first one is to appreciate that faults are natural features and how they react and act. The second, like I say, very, very brief, 2-minute introduction to fault seal. I'll speak about the scale of observation that we're using when we look at seismic interpretation, and then I'll finish by explaining something that is a truism, no matter what company you work in, no matter how much experience or expertise you have. All maps are wrong. They can never be right because they're a representation of something that we can't really know. So when you start from a position of knowing that your map is wrong, you're already armed to make it better. And I think that's a really important, that's where I start from. Even when I finish my map and I've done all my structural analysis, I still know it's wrong, but I've done the best that I can with it and with the data that I have. And that's an important mindset and a change maybe that hopefully I can get all of you guys to buy into, let's say. And I thought I'd start today by looking at your logo, the NAPE logo. It's really cool. I really like it. And it's a simple kind of a cartoon representation of Nigerian play, and some of your most important fields. And you may or may not be familiar with this quite old picture now from Weber, I think 85. And the cartoon, obviously, in reality is a little bit more complicated, as you would imagine. You have oil in black and gas in green, and you've got stacked reservoirs, and some of these reservoirs are filled to spill. Some of them leak across the fault. Some of them are sealed by the fault and are filled more than the structural spill because it's such a good seal. And the whole thing is charged by migration up this fault and then, you know, charging into the traps. So you've got faults acting as three different things. They're a conduit, they're a seal, and they're a leak. But it's all the same fault. So you kind of get an impression that faults have a lot of different character and are also temporally constrained, doing things at different times. And to talk about the timing of these things, how fast do you think migration occurs? Kind of a question that maybe you don't ask yourself often, because migration is kind of just thought of something that's happened in the past and maybe even it's happened present day, but you don't really need to think about it. This is looking into the face of a fault in the seismic that was shot in it's Gulf of Mexico, but what you're looking at is extremely high reflectivity in the hot colors there in the circle of the face of that fault. And this was seismic that was shot in 1985. They then drilled a well and it went through the part of the fault that I'm pointing at with my arrow there. And they drilled that about 7 years after this image was taken. And they hit the same reflectivity, but it had moved. And the fluid pressure when they were drilling this just went off the charts. It was dangerous. It was so high. And the reason is the fluid had migrated 1 kilometer up the fault in 7 years. So that's kind of like, you know, if fluid can move 1 kilometer in 7 years, geologically speaking, migration happens like that. So faults as conduits, that's fast. But we don't, sometimes we want the fault to charge, but then also we need the fault to maybe seal, or maybe we need the fault to leak. So there's quite a kind of a dichotomy that we have to hold in our heads when we analyze these things. So let's take a step right back and think about what a fault is. Here I'm building up a nice succession of sandstone, shale sandstone, and I'm going to fault it. And that's a fault happening in 3D, right? That's how a fault happens. And if I slice this like you'd slice a cake and kind of look in to this part of the fault, then hopefully what you'll appreciate is that when we look at a seismic section, we're only picking the fault at this exact point, and we're representing this point, this fault, this three-dimensional object, we're representing it with a line. When we look at a map and we look down on top of the fault, and you're all familiar with looking at maps, hopefully, then we're also representing the fault with a line. The line might be here or it might be at the divide. It doesn't really matter where the line is. What matters is it's a 2D representation of a 3D object. And these are the currency of the industry sections and maps. So I'll come back to that in a moment. I want to talk about how faults seal for a second. And this is a nice clay sandbox experiment where we set this up in a lab and we let it run, and you can see the dark bands there of shale, and they smear as we fault this sequence. It's not like there's a real clean break. I mean, it just kind of smears through the area that we think of the fault as being in. But again, you kind of struggle to represent this with a single line. And smears are just one of many fault sealing mechanisms, but they're a pretty effective one. Here's a smear. This shale up here on the left, if you can see my cursor, hopefully, is this shale down here. So we've faulted this down here, and we're in an outcrop. And look at what's happened in the middle. The shale has kind of just smeared and fallen into the fault zone here and been dragged along it, and it forms a kind of a membrane at that point. Now, if this sand here was our reservoir and we charged it, it couldn't get out. It has nowhere to go. There's shale here, and shale is impermeable, and it's just it's stuck there, and we call that a juxtaposition seal. And in the main, juxtaposition seals are the most effective type of seal you can have. When you're prospecting, when you're thinking about your prospect or sealing, the number one thing you want is juxtaposition seal. However, there is another type of seal. If we were to charge the upper sand, so you can see the sandstone here and imagine charging it, the smear might hold back some, if not all, of that oil. And we would call that a membrane seal, because a membrane is permeable at a point, but actually quite effective at other points. And how effective it is depends on its capillary threshold pressure. So a bit of a complicated term for something that's reasonably simple. If this is your membrane, and we start over here on the left, we've got a droplet of oil or gas. In order to get from here out the other side, it needs to change its shape so that it can fit through the membrane. But it's not going to change its shape on its own. It's going to change its shape because it's under pressure. And the pressure that's required to change its shape enough to escape is the threshold pressure. We can show this in a very simple experiment by virtue of using a sieve that you'd use for sieving flour and a fishbowl. Now what we do is we turn the sieve upside down, we put it in, we take the fish out, we put it in the fishbowl, we get a pump that's going to pump air, and we put the tube into the fishbowl and under the sieve. So what we've done in effect is set up a trap. The sieve is our trap. It's a four-way closure, if you like. We've created a source with the water pump. We're charging the prospect with our tube, and that charge could be a carrier bed or it could be a fault, but it's the mechanism by which the gas gets from the source to the trap. And then we need it to seal. So I talk about membrane seal in terms of faults, but also this is true of top seal. So you could think of this in the same way, right? If you need a membrane top seal, this is exactly the same principle. And the seal is going to be formed by virtue of the fact that the holes in the sieve will require the gas to change its shape, because the holes in the sieve are so small that gas needs to change its shape to get out. And it can only do that if it's under pressure. And where does the pressure come from? Pressure comes from the gas column. And the taller the gas column, the more pressure you have. And therefore, if you've got small holes in the sieve, you need a tall gas column. But if you've got big, massive holes in the sieve, you need less of a column. And that's what tells you how good your seal is or not. How big are the holes in your sieve? So I can run this as a video, and you can watch the trap filling with gas and then failing, breaching at the capillary threshold pressure. So there it is, filling up. And it's a remarkable amount of gas to hold before failure. But failure will occur because at some point pressure is too much for the interfacial tension across those holes to hold. Bang, failure. So that's how fault seal and how, essentially top seal as well. And it's good to keep in mind how that process works when we talk about the next part of our talk today, which is the scale of observation that we're using. Because what I showed you earlier when I showed you the smear was a little sandbox. I mean, you could put your hands over the top and the bottom of that. That's not what we're looking at. In exploration prospecting, we need big faults to hold hydrocarbon on a commercial volume, because that's what we want to drill. We don't want to drill non-commercial volumes. We don't want to drill dry holes. We want commercial oil, gas. That's what we want. And therefore, we need good size faults to support that. So if you walked into this quarry, hopefully you've been looking at this for a minute, and you would think, wow, that's a pretty big fault. And that's about, as big a fault as you're going to see quite a lot of the time when you work in the field, because this quarry has a great exposure. But the displacement on this fault, the amount that the fault has moved the rock, you can see the reds come down, the oranges come down to here, the blues come down to here, and it's a bit segmented through this section, but in total, it's about 15 meters displacement. So if you were to take a normal bus, you could probably fit that bus 3 times on top of each other into the displacement, so that the amount that it's moved in that quarry. Now that's different from the total height of the quarry or the total height of the fault that we can see. The fault height here is 60 meters, and I would argue that the fault itself is bigger, except we've got an unconformity at the top that's shot the top off, and we can't see below the quarry floor. So I think the fault is even bigger than 60 meters, but the displacement is only 15. Now, what would that fault look like on your seismic? That bit there, not the whole fault by any stretch of the imagination. That's about a 15-meter displacement fault, and that's about the height of the quarry. When we're looking at seismic, we are on a completely different scale to looking in the field. I mean, vastly different. If you think about that fault isn't going to hold you a hydrocarbon volume worth drilling. What we want is this size fault. We want big faults that we can drill behind, because that gives us a big juxtaposition or more opportunity for membrane seals. So how big are these faults? This is a lovely example because it's a kind of a wave building from South Korea. And it kind of could be thought of in the same way as just cycles in your seismic. So you're used to seeing the wavelet in seismic, and you're used to following the positive through the zero crossing to the negative. You could probably, in some seismic, pass a couple of cycles in the height of this building. So what I'm saying is you can fit that building into the displacement of that fault, not the total height again, just the bit that's moved. And if you were standing on the street looking up at that building, you would realize, wow, okay, when we pick faults in seismic, we are picking huge objects. And faults, much like this building actually, are not flat plains. They have character, they're natural features, they exist in nature. And as the architect Anthony Gaudi said, there are no straight lines or sharp corners in nature. The trap that's on the right here is a lovely representation of the intricacies of the natural variations in shape along a fault surface. And that's kind of what you need to have in order to do a good juxtaposition analysis. You need to appreciate exactly in three-dimensional space where your reservoir is and where your seals are. So Gaudi was responsible for the Cathedral de Familia and also all the really cool architecture in Barcelona. And he wasn't fond of straight lines or boxes. So he probably wouldn't have liked what we do with faults, which is quite often we might build them even as nice as this, but then we turn them into this. And it's a poor representation of their nuance. It's a bad, replication of their structure. If I'm allowed to take the architecture analogy a step further, I would say that you've been looking at this for a few moments and you probably know that that's a nice architect's drawing of a house. Now, I am guessing, but I don't think we have any qualified architects in the audience, do we? We maybe somebody's done architecture and then come out and gone into geology, but for the most part, geologists are not qualified architects. You wouldn't be able to draw this blueprint and have that building built. You wouldn't pass the regulations to do it. But if I showed you this picture of a house, you would immediately know that's a bad drawing. You know for a fact that you can't build that because it'll fall down. It's an awful drawing of a house, even though you don't have the skills of an architect, you know that. However, if I show you these two maps, do you instantly see the right and the wrong in these maps? Most people don't. It's just not a skill that we have. We don't see maps like we see houses every day. We don't have that conceptual jump from seeing a map and knowing really what it represents. So we have to kind of use as many tools and tricks as we have to make sure that the map is as good as possible, because we don't have that visual acuity of saying good, bad. The map on the left is bad and the map on the right is good. And the main difference is this fault doesn't connect in the map on the left. On the right, it does. And what that does is it completely changes the contours between this side and that side. So if this was your trap and you were trying to charge it, you would have a complete conduit up to charging it. Whereas if this was your trap now, you can't get across this fault and you can't charge it. So it makes a huge difference just changing a fault correlation. But I'll go one step further. The reservoir map on your wall, on your computer, wherever you have it, is just a floor plan. It is one level and it cannot exist in isolation. Even though we get very focused on it, a good floor plan is absolutely based on a good house architect's 3D drawing. It has to exist within this. It cannot exist in isolation. So you need to build a house. And it's not just a house you need to build, because let's go back to our fault and think about how big was the fault that I showed you first time. Remember, the quarry fit into about my circle and the fault that we thought was big was small. If I was to look at that fault from the street, it would be the Petronas Towers in Malaysia. You know, that's a 450 meter tall building. You are looking at one level of that when you look at your top reservoir map, and that's the size of the faults you're picking. So it's mind-blowing when you when you realize it, because you never see these faults in the field. I mean, you'd never see a fault as tall as the Petronas Towers in the field. It's mad. But it's easily the size of this fault here. It's not like this fault that's the conduit that our whole Nigerian system at the start was based on is taller than those two towers. That's mad. I mean, you know, we are dealing on a huge scale with natural features, and then we turn them into boxes and we think that we're doing the best job we can, but we really need a mindset shift in order to not just use the sections in the maps, but the three-dimensionality of the fault so that we can build a good map. Because otherwise, if we're not using the three-dimensionality of it, maybe the map isn't as good as it could be. And there's another complication, which is when we pick on a section, and this is, you know, this is an event and we put the stick where we think the fault is, we are only looking at a part of the map. The map is in depth, so you can probably see the green here and the blue here. I'll color the section in depth as well so you can get your eye in. So this is the high bit in green, this is the low bit in blue, and the black thing there in the middle, that's your fault. And then what you do is you do a few sections this way, you do a few sections this way, you correlate them together and you make your map and you make your fault on your map. But what's this? The distance between where we let our horizon stop here and we started here, that's what we're seeing as the black space on the map. It's called, the technical term for it is called a heave, but the reality of it is when you look at a map, you are not seeing this information. That is hidden from you, and you have to mind the gap, because believe it or not, the empty space that is the black polygon on your map is where the most valuable information is found. Once you get your mind set in that, you can build really much better maps. So here's a map from a trap in the North Sea, and it was drilled a couple of times. And now what hopefully you're seeing is the black space. So what do you think this big black space represents? Well, clearly you would now start to think, okay, well, that means the gap must be really big, which means the fault must be really big. The fault has to be big in order to have that much heave, unless it's incredibly low angle, which it isn't, because we're in an extensional environment and all the faults are about 60 degrees. So we would expect all of these, the thickness of the gaps, to represent the size of the fault. But is that always the case? And what if it isn't? What if we've got big, thick gaps, but not much movement across the fault? Then we've got a problem, because why would there be such a big gap if there wasn't such a change from one side of the fault to the other. So I'll show you the section from the same map, and I'll draw your attention to this bit down here because they had a discovery, but they were thinking, could we drill this compartment? Well, they could, but they'd be in trouble because they need the green bed to be a carrier. And so the green bed carries it up, and then they thought, well, maybe we have fill all the way down to here. We don't really need this fault to seal because the oil could be all the way down here. But is the green a carrier bed? Well, hopefully what you've seen is this. What's going on here? Should there be a fault there? Because I can see something in the seismic, and then the green bed goes, junk, takes a jump down. So should there be a fault? Well, I don't think we can justify a fault. Look at the yellow bed. Remember when we were in the quarry a second ago and I said the yellow bed comes down 50 meters, the green bed comes down 50 meters, the pink bed comes down 50. This one doesn't. The yellow bed is huge movement, but then the green is almost no movement at all. So we have a problem because that's not a fault. But what's happened is the auto tracker's been busy, come along here, hit this kind of disparity in the seismic and jump down here. And actually what it should be is that the green event should be here. That is a wrong event. So in this case, the fault is correct, but the horizon is wrong, but the answer was in the gap. The answer is, there's so much value to be had from that blank space. And now if you need your green to be your carrier bed into your prospect, then, well, maybe you're in a little bit more trouble. And it's not just maps like that. All maps are wrong. And I can kind of show you in a few examples. I'll do this quite quickly. Here was a field that was found on 2D seismic. The green represents the 2D grid of seismic that was shot at the time. And the map is the correlation of the faults that they were able to pick on that seismic. And they thought the field looked like this. And they started drilling and they started producing, and then it was a good field. So they shot new seismic. And when they did in 1991, so about 15 years later, they found that the faults actually don't correlate like this at all. They're north-south. They're not this kind of northeast, southwest orientation at all. It's a completely more complicated field with a totally different fault network than they thought they had because their map was wrong. And this map is wrong too, but it's better. And BP found this. This is a BP field in the Gulf of Mexico. And it started with, and it's deep and it's subsalt, fair enough. But once they started drilling, they started putting more faults on because wells weren't communicating with each other and they realized they had compartmentalization, they had different contacts. When they eventually shot new seismic, they had a really complicated fault system, and that still wasn't good enough because every time they drilled wells, they put new faults in and they improved their understanding of things. And I can tell you as well, having seen it, there's more recent seismic and that map is wrong. Okay, so all maps are wrong because they're a moment in time and we don't have the full appreciation that we should have. Even with good 3D seismic, we'll still make a wrong map, because we're always going to be limited as well by the resolution that we can look at. Here's a coal mine with 20-meter faults mapped in it. And the coal mine was mapped by people on the ground. So this is as accurate as you can get it. And the 20-meter clipping is meant to kind of, is an expression of what you would likely see in good 3D seismic. So those faults are what you would see in good 3D seismic of this mine. That's the mine. If you put in all the faults, it's a lot more complicated than it looks on the surface. And any of those faults, and especially this unidentified, really high density crossing damage zone, could be detrimental or beneficial to the flow in your reservoir, but you're never going to see it. And you're only going to see it in expression of flow between injectors and producers and all that rich information that you get when you develop the field. But when you're prospecting and you're looking at your field for the first time, you are way off. And this is happening all through time. This is, since 79, principal reason for dry holes, incorrect structural interpretation. 380 Amoco are an old company that they've now wrapped up. But when they looked back at 380 of their wells, the most common reason for failure was trap definition. The worst defined risk parameter when we looked at it was trap definition. In 2015, we looked at 97 wells at Christian Mathieu for the OGA. Trap was the main reason for failure, and lack of lateral seal and lack of trap in structural traps. And the Exxon guys looked a couple of years ago at 20 years of Exxon drilling experience. I think there was something like 500 wells in this or something. And the dry holes and structural traps, 52% of the time could be down to trap seal failure. So this is not new, but this is a problem that we continue to have. So let's take you back. I promised I'd take you back to this and tell you what you can do with the fault. And again, we'll look at the fault being, growing and all the rest of it. And then we'll look at it in 3D. And we'll stop it there, and we'll see that, we've sliced it like a cake, but it is this three-dimensional object. And that is expressed like so. Hopefully you can still see the fault being formed here in the middle. And if we were to look at the throw of that fault on a graph, it would make a lovely arc shape like this, because the most throw would be in the middle and the least throw would be at the tip. And what we call that's a fault plane profile, and it's very powerful. And the most powerful part of it is the simplest. If we think about the throw on this fault, then about 100 meters is the height of the throw, and that's the biggest part of this fault. So if we were to kind of color that in on the fault surface, we'd have the red highest polygon or expression of throw in the middle, and then it would get less and less and less. And we're down to a lot less throw now until we get to the tip of the fault and we have no throw, because we're back to where the rock is intact again, either end of the fault, and there's no fault left. But we've created this, what we call a bullseye diagram, but it's a 3D expression of the fault, and it's really powerful, because what we can do, and we have done, and it's not us, this was Schultz et al., but what they did was put together 10,000 faults from all over the world, and what they were doing was mapping the length of the fault, which is this parameter, and the height of the fault, or I take that back, the displacement at the maximum part of that fault. And it's incredibly regular the world over, because faults are natural features and they have to obey the laws of physics. And this is the laws of physics in action. You can't have a fault that's too long for the amount of displacement that it has. And if a fault is a certain length, it can't get bigger without getting longer. That's the crux of it. If you want that fault to be bigger, you have to make it longer. Otherwise, it starts busting the laws of physics, and that can't happen. So if you were to take your data and plot it on here, and you plotted a fault out where my arrow is, what you're saying is, I've got a really, really, really big fault, but it's just not long enough. It's just too short. In kind of, in squishy terms, it's kind of like this. It doesn't make sense. No fault would act like that. And if your data was to plot down here, the fault's way too long for the little displacement it has. It has no reason being that long. The tip wouldn't propagate out that far if it was this small. So what you've done is you've made a really long, short fault, and we see that quite often in overcorrelation. If you had, several small faults that were all this size, but then you correlated them all together as one big long fault, you'd get the data plotting down here, because it wouldn't, their little size wouldn't justify being that long. They're just one very simple tool, but there's lots of them, and they can all help to improve your map. So how do you use this tool? And this is kind of where I'll finish the talk, basically. The correct mapping workflow is, and this is from the Horda platform in Norway, you're looking at about 40 kilometers by 30 kilometers of fault network here. It's a brilliantly crafted fault model from Polvip at Equinor. And what you're looking at is a lot of fault segments. You correlate those fault segments into fault surfaces, and you join those fault surfaces where they join. Faults join in the subsurface. They must do. That's what they do in nature. So you have to express that properly in your model. Then you add in your raw data. It could be an auto track. It could be your own picking. And where the raw data hits the fault, that's your polygon. Simple, it's an intersection. It's just where the raw data hits the fault, it's a line, and now you have lines that you can use in maximum displacement length plots, in fault plane profiles, which are incredibly powerful, but a kind of another talk for another day if you like. There's a lot more information in those because you can use them in arrays as well. And you have the ability to use loads and loads of different tools when you have these polygons. And if you find that the polygon is telling you you've got an incorrect gap, basically, because that's what they represent, then you iterate. In the example that I showed you with the seismic a minute ago, we had to move the horizon. But maybe it's that you have to move the fault. It doesn't matter. You move it. It's all to improve the product, but that's how you create a house, because the empty space, the gap, these polygons, they are the load-bearing structures of your house. These are the cornerstones on which you have to build your map. It's at that point, once you have gone through that iterative process, that you can hit make my surface, and wow, like this is a beautiful map. This is absolutely as close to perfect as you can. I said all maps are wrong. This is as close to right as you can make it. And it's still wrong, but it's really, really good. And it, you know, you could drill on this, you could use this for fault seal analysis, you could use this for making your interpretations, all the rest of it. Now you've got a map that's worth investing time in. Now you've got a floor plan that you can stick on your wall, and you know that it's only one part of a building, maybe the size of the Petronas Towers, but it's as good as you can make it. So I was going to give you a little exam at the end, but I realize I kind of am running over time. But just to kind of give you a very quick show of this in action. On the left, you have a map of a discovery that was relinquished by the company because they thought it was too small. And the polygon that I'm drawing is what they thought their prospect was, because they drilled a discovery and an appraisal well. They thought that was their prospect and they walked away from it. They sold, a company picked that up and they brought us badly in to look at the faults. And immediately we noticed that that fault didn't exist, because faults don't, you know, they don't act like that. There was a saddle through there. And that this long fault was plotting low on our length displacement cross plots. It's over correlated. It's actually, look, it's three segmented faults that had been joined as one. But when you take away those two faults, what's their discovery? Bang. Like, I mean, you've completely changed that prospect from being walk away small volume to huge, just by virtue of fixing the map, the faults. So you can spend a long time in your analyses and in your discussions on the hydrocarbon in place. And we do need to spend a lot of time on net to gross and porosity, recovery factor. Don't forget about GRV. The GRV, the gross rock volume, the amount of rock that you have, is based on your map. So if your map is not correct, like this one, you could be walking away from a lot of volume, or you could be overestimating volume. It works both ways. So I will leave it there, but I will finish by saying we are a consultancy based in the UK. We have been in operation since 1990, building software and providing services and publications to the industry. We're highly published in the literature. And we've been concerned with creating good maps, doing good structural interpretation, seismic interpretation, fault seal analysis, and we can, you know, we look at fractures and we look at geomodeling. We have, you know, the whole gambit in here, but we're hopefully a pretty well-respected consultancy. And having worked myself with the biggest companies in the world and the smallest, I can tell you all maps are wrong. Even in these big companies, they can all be made better, and so can yours and so can mine. But it's about getting into the mindset and explaining to people in your team, we can do this better and it will be better for everyone. Because trust me, the map also is how you make your cellular model. That goes into your simulation, and then you try to run history matches. But if the map is wrong, the cellular model is wrong. I mean, the cellular model is wrong anyway, because it's full of sharp lines and corners, and we know that those don't exist, but it's more wrong if your map is wrong. So if you want to contact me, I'm more than happy for you to come directly to me, or you can go to the guys at NAPE and ask them to put in touch. I'm on LinkedIn, obviously. I'm under the Badleys logo, and you can get that from the NAPE announcement as well for this talk. But I think I've pretty much run exactly to time, and it allows us time for some questions and hopefully some answers. So yeah, I'd like to open that up to the floor, and I really thank you for your attention this morning. I realize I kind of threw a lot of information there, but hopefully I provided enough pictures and enough, you know, moving images to kind of hopefully leave some of this stay with you beyond this talk. So yeah, I'll give the floor back over to my invitees, and a special thanks to Ehi for inviting me to speak today. It's been a pleasure talking to you, and I hope to answer your questions now.
Thank you, Dave. Beautiful presentation. Without too much ado, we have a couple of questions already on the Q&A.
Hit me, yeah, please.
Top, and I'll be taking the first one coming in from Majid Olabi's examples of reservoir rocks. How do oil and gas get trapped in reservoir rock? I'm sure you've seen the question here. So let's deal with that before we go on to the next question. Yeah. Look, I mean,
these are the fundamentals that don't go out of fashion, right? Like, you know, what's your source rock? Well, it's got to be high in organic material, and there's loads of different source rocks, and there's classic ones that are known throughout the world, and there are ones yet to be discovered, and we don't really know everything that we'd like to know about source rocks. But the important thing about source rock, I think, is, apart from the high organic content of it, is that there's enough of it. Of course, you have to cook that up then, because all the little organisms that have died and been preserved in that shale, let's say, are sitting there, and they're carbon life forms that have died, but the carbon's there. And then you have to cook it up, so you have to get it hot. So you need a kitchen. It's called a kitchen. That is a temperature that is optimal for cooking the organic content so that it becomes hydrocarbon. That's the oily residue that we're looking for. And once it starts cooking and starts separating from the shale, it becomes buoyant, because remember, oil will sit on water. So if you're in an aquifer, the oil will want to get to the top, and that's when you get mobilized. So, you know, the hydrocarbon is in the kitchen, in the source rock, it gets cooked. You don't want it too hot, you don't want it too cold. It's a kind of a Goldilocks thing, right? Because if it's too hot, it'll cook it and kill it. But if it's just the right temperature, some temperatures are optimal, and some source rocks are optimal for oil, and some are for gas. And you go through a gas window, you go through an oil window, and you get, hopefully, migration into your reservoir rock. So what's a reservoir rock? It's something that's porous and permeable enough to store the cooked up oil that we can draw on. And most of the world, you're looking at sandstones. Porous carbonates are another big source rock around the world. And there's even reservoir rocks. There are even igneous and even basement reservoir rocks. And the last bit is, how do they get trapped? That's the key, right? Because hopefully, if you have a good understanding of your play fairway, you know where your source rocks are. You might use some geophysical tricks, like you know, to tell how hot the source rock might have become, and therefore whether you have migration possible or not. But then once you get those parts of the system moving, you need to trap it. And you need something like the sieve. You need a closure. It could be a four-way closure, like a fold, or it could be a stratigraphic folder. So you might have your reservoir rock planed off by an unconformity, and then the shale sits on top. That's a good trap. Or you have a fault that moves a reservoir so that it either has a juxtaposition seal or a membrane seal or both. And that is the trap, the container, if you want to think of it that way, that you pour the oil into. The oil displaces the water, just like in our video with the sieve, it pushes the water out, which increases the pressure. But as long as your trap is good, it will hold that pressure. You drill it, and we all rejoice, because that's what we're here for, right? We're here to find oil. That's the whole point, and gas, and to you know, and in doing so, add to the portfolio of our company, add to the prosperity of our country. It's an important thing that we're doing. You know, I know there's a lot of pushback about the oil transition or the energy transition at the moment, but the world needs oil, and countries need to be prosperous in order for their people to have better lives. So let's get out there and find oil and make that happen, because, you know, as much as the energy transition is something that's happening, in the meantime, we need energy, because we're not there yet. So let's go and find some more oil. That's what I say to that. Hopefully that's answered your question. It's yeah, it's a big one. So if you like, I'll move on to the next in the Q&A, which is how do you identify fault dip direction from the seismic and the structural map? Very good. Okay.
Yeah. All right. I think correct.
Yeah. Go ahead, please.
Yeah. No, I'm happy to throw it back to the floor if you want to.
Go ahead.
Yeah, the fault dip direction, what you can do is you can create attribute maps. So it's an attribute based on the curvature of the map that you've created. And what you will automatically extract from those is the dip of the faults. So when I showed you where the gap was a while ago, I had a horizon on this side, a horizon on that side, and the fault was here. Well, if the fault is there, that will show up as a hot color and a direction. It has an azimuth as well as a dip. So you can automatically extract that. If you've got a map right now, you can extract dip like that. All you need to do is run a dip attribute analysis and you have it. You know, in the simple terms, you can probably visually get better at seeing what your dip is by looking at the color on either side of it. So if you've got a depth map with red as high, shallow, and blue is deep, and if this is red and this is blue, well, that means that this is high and that's low. And therefore the fault has to be dipping that way. If it's a normal fault, it's got to be dipping that way, because how else would you get high and low on this way? So once you start getting your eye in, you can actually become much better at reading maps just by looking at the color on either side of the fault. And then once you get even better at that, you can start looking at the contours on either side of the fault. And that's when you're really at ace level map interpretation. You look at the contours either side, and in your mind's eye, you can see the shape of the fault and how big it is. But that's, yeah, not a lot of people do that or can do that. It can be learned, it can be taught, but it's just not something that we do, you know, natively. It's like going back to that picture of the house. It's not something you would see good or bad straight away by looking at it. You need to kind of learn that skill. You can see Gideon, if you want a question.
We have a question there. Thanks for your wonderful presentation. He's asking if there are, please elaborate more on the Cobra example.
I can do better.
Any more appraisals, drill sense?
Yeah, if you look, well, on the thing there, I flashed up the the reference for this. It's Breton, B-R-E-T-A-N, 2014, I believe, and it's published. That example that I showed you has been published. So the company that that brought us in is called Premier Oil. I'm sure you're probably familiar with that name, and Premier have a big presence in the UK. I can't say much more about their drilling campaign without breaching confidence. So as much as I would like to tell you the end, I am hoping that we can bring you that in another publication, because it's definitely worth publishing, I think. So unfortunately, I can't tell you what the results of the appraisal of the rest of Cobra was, but hopefully soon is the answer.
That's fine, Dave.
That's fine. Yeah, there's a lot of good information, and actually you can probably, you know, almost tell what the answer is going to be if you read the paper, definitely.
Okay, let's go quickly. I think our time is really ticking. So you probably need to merge two questions into one. Please, can you explain the relationship between the heave of a fault in maps and in nature? And then probably take along the second one with you. What is the approach to building the right velocity model for converting the time map to depth structural map?
Yeah, these are all, yeah, very, very pertinent questions. If you think of, if you can see my, hopefully, let me just move this and hopefully you can see, if you're watching the video, you can see my hands. Let's say that that's the unfaulted structure and then we fault it. So that's high, that's low, and that's our fault in the middle. The throw is the vertical component. The displacement is the dip slip component, and the heave is the horizontal component. So when I did this with my fault, the distance between the end of the horizon on this side and the end of the horizon on this side, this bit, that's the heave. So it's the horizontal component of the fault, and it is exactly the gap in your map. It is exactly the width of the polygon of the gap in your map. So it would stand to reason that if you have a big heave, you can only create that with a big fault, because you see, if I've got a small fault, I have a small heave. But if I have a big fault, I can have a big heave, and then I should have a big gap in my map. Hopefully that's that. And the correct, wow, another big question, velocity conversion. What you ideally want is a density log from a nearby well that describes the sequence of rocks that you're going to get through if you're going to drill on this map. And therefore, you can use the velocity intervals of each of the layers that you think you have in your area to convert the time to depth. And it's a real skill. And there's more to it even than that. But what I would say is each layer in the sequence, so if you're drilling down and you hit sandstone and then a carbonate this size and then a shale and then some salt and then a shale, you need to know the velocity of each of those parts, because the time has gone slow, quick, slow, quick. And therefore, when you get to whatever millisecond, 2,500 milliseconds you've got, the wave has not got there in one go. It's been slowed down and sped up through the different rocks. And if you know the conversion factor for the velocity of each of those rocks, then you know how deep the wave has actually gone. That's hopefully the kind of helicopter approach, I guess. But it's a skill in itself, and it's a big uncertainty.
Okay. In analyzing the sealant efficacy of fault, can fault slip data be analysis?
Yeah, good, really good. Yes, it absolutely can. And we have, our software was the first software in the world to do this. And it's about using either the paleo stress, if you want to look at the fault as it might have acted through time, or the in situ stress if you want to check it now. But the movement along that fault is absolutely down to stress, right? That's why faults move, because they're stressed. And in the moment before they move, the moment just before the seismic event, that's when it's at its most critically stressed. And you can analyze that by looking at the three components of stress: vertical, SH min, and SH max as they occur in the horizontal, and calculate those on the fault surface. And then faults that are optimally oriented for critical stress in that stress scenario, be it ancient in a paleo stress or present in the in situ stress, a fault will only move if the stress allows it. If the components mean that it can move and it's under pressure, it'll move. And you can check whether the fault is orientated correctly or not. And it's actually something that we've used to devastating effect in field development, because sometimes you want the fractures to be pumping fluid, because the hydrocarbons they're actually in the fractures. That's where they'll move through, because the matrix might be tight. So when you start developing, you want to actually develop out of the fractures, and you want the fractures that are critically stressed. So you apply the stress to the fractures or faults, and you find out which orientation you want to be drilling in. It's actually the way that we develop unconventionals. When we frack things, what we're looking for, when we frack an unconventional and we break it, it will break in the orientation of critical stress right now. And therefore we need a drill sweeping through the correct orientation to pick up as many of the fracks that we've created as possible. So excellent question. It is actually, you know, really widely applied. And like I say, we were the first to do it, and we still do it today, and are very happy to talk about how we could do that with the at another time. Definitely, big question.
Dave, the questions are coming in by the second, so I will pick some. And if we're not able to exhaust all the questions, I'm sure with the permission of my chapter coordinator, you may need to come in again. But let's take this interesting one. As a structural geologist, how often do you invoke your knowledge of prevailing tectonic setting to create a fault framework, especially in areas of poor seismic resolutions, limiting fault interpretation? This goes with the other question, which I think they're synonymous to each other. What is the best way to avoid wrong fault identification?
Yeah, okay. In answer to the question, how often do I use regional tectonics? Every time. I mean, what we know needs to be applied. Like I did a project only last week where I was basically putting all the literature together and explaining to a team that were prospecting, this is what we already know, you know, and you would expect the faults to be at least reactive to the big movements. And they might not react the exact same as you think, right? Because if you've got, let's say, a major north, south, east, west system, well, it's not necessarily true that all the faults that you're going to create are north, south, or east, west. There's other factors that might control their development, and maybe they are kind of, you know, at an angle to that, but it's predictable, and we should use definitely what we have. And in answer to the question, how do we make our fault interpretations better, we need to start picking polygons, and it's kind of not really in a lot of the workflows that we use. Typically, the workflow now is we create an auto track, we create the map first, basically, and then we pick the faults after, and we kind of just trust that that's correct, but we need to use those faults and the gap and the information that's within those to make sure that the auto track's done a good job, because the auto tracker, and if I leave you with one other thought today, the auto tracker doesn't know anything about geology. It is unintelligent in the extreme about geology. It is following signal. It's following time. And if you think about it, time is not the same as the rock. It's not the same thing. So you are the geologist. You need to interpret that signal into geology. When the auto tracker creates a map, it's not a map. It can be used as one as long as it's QC'd, but it's not the finished product. And I think that's where the industry has become at its most pushed by software, I would say. We've got huge amounts of data. You can't pick it all. You need the auto tracker to do that for you, but we've kind of forgotten about that step where we check that we make sure it's done a good job by looking at the faults and making sure that when it jumped down and onto the next level, it did that correctly. And you can only do that by assessing the polygons, the intersections of where the fault surfaces and the raw data meet. And that is, if you take away one thing, it's you know, if you're not using polygons, if you don't have a fault interpretation part in your workflow, you might be missing out on something that could really help and really improve your chances of success. And as regards all these questions, I'm delighted. Look, by all means, if you're happy, send them to me in an email. I'll answer them, and you can put them back to the NAPE group on your website or something. I'm delighted that people are engaged and asking.
Okay, but before you go, I'll take two more, and then we'll let you go.
I'm happy.
Okay then. There have been many publications on sill analysis, which is dependent on the fault throw traps. What is your advice? Any future fault sill analysis work And then the second one from George, I'll imagine it with this one. What software can someone use to run a good fault analysis? Fault silt analysis. What does someone need to know to understand fault silt analysis? So after this, then we'll let you go.
Okay, two excellent questions. The fault seal publication record, Badley's, the company that I'm representing, are the public, we published the algorithm that the whole industry uses. It's called shale gouge ratio. If you've ever heard of SGR, that came from Badley's. We published that, and we also published the ability to convert shale gouge ratio, which is in essence just a description of how much shale is in the fault zone. So SGR is a kind of an averaging of all the country rock as the fault is developed. And at any point in the fault, you can check how much shale is likely to be there based on what kind of rocks have moved past it. SGR on its own, though, doesn't always necessarily tell you if a fault is sealing or leaking. In order to do that, you need to convert the SGR into a trappable column height. Remember when we had the gas column in the sieve, that is the pressure that's going to fail the trap. And that's what we need to calculate, actually, not the SGR. We need the pressure and the column that that pressure represents. There's two ways of doing it in the industry, and one of them, which is the most widely used, I think, in most of the companies that we deal with, was created by Badley's. It's called the Yielding Algorithm 2010. And again, Badley's have led the way in the way fault seal is applied, you know, since we started doing this back in 1997, which was the first time it was done. Is there software to do it? Yeah, you're looking at it. We have been developing that software since 97. Since we started developing the science, we started developing the software to do it. It's called T7. You might have as called Trap Tester in a previous life, but Badley's provide that software. And if you want to connect with me on LinkedIn or through my email, I'm more than happy to talk to you about how T7 is, I have absolutely no fear in saying it is the best, most comprehensive toolkit for fault seal analysis in the industry, because that's what it was built to do. There's other systems that do fault seal analysis, but it was kind of shoved in there later, but we don't make any compromises. So yeah, happy to talk about that. And like I say, happy to answer.
Thank you, Dave. To round up my own small little portion is I'm taking something with me. All maps are wrong. The map, yeah, all maps are wrong. And there are no straight lines in nature. And it can't get bigger without getting longer. Huh? So, and then finally, the map is how we get the simulation model. So if the map is wrong, the simulation model will be wrong. Thank you so much, Dave. I hand over to Ehi Mbazwe, the chapter coordinator.
Thank you very much.
Thank you very much, Dave. I don't know, there's a hand up. I don't know that we can take their hand. Well, before we can just hang off, please. We'll still take your question. We'll still take your, but let's just be able to move on a bit. I will get that. Thank you very much, Dave, for the wonderful presentation. We also will just want to pass on this now to our publicity secretary to just take a few announcements before we go on. So, Tuwasun, hand over to you, and then we'll make a presentation to Dave for a wonderful presentation. Tuwasun.
Right, please, can you confirm that you can hear me? Hey.
Yes, loud and clear.
All right, and you can see my screen as well.
Yes.
All right. Thank you, everyone, and thank you, Dr. Dave, for a very insightful presentation. So just a few announcements for our members. Today is the 17th of June, and the Abuja technical presentation is currently what we are having. However, this evening, we would also have the CPC, the first meeting for the CPC committee meetings. This is a series of meetings that we typically have prior to the conference, and it's to enable all committee members to come together, share what their milestones are and how they are able to achieve their deliverables. If you're a member of any of the committee, please, you are enjoined to connect to this meeting, and it will be at 6 p.m. So I'm just sharing this calendar so we see a snapshot of all the activities that we have planned for this month. I have also for July, but I'll just gloss over those very quickly. So call for abstracts. The EIC has mentioned that we are getting good abstract. However, there is still room for more. As you know that this is a technical conference that we'll be holding in November. The sub-teams are as highlighted. When you go on the NAPE website, you will see the link to submit your abstract and the detailed requirements that you are supposed to fulfill. So please, you're enjoying this 2 weeks time to do. It closes on the 30th of June. So please ensure that you're getting your abstracts early. If you need approval from your organization or your bosses, please ensure that that is also proper on. I don't know if the VP is on the line. I think I will want him to emphasize on this after I finish the basic announcements, but there is a critical need for us to please send our submission in. 2 weeks again, this closes on the June 30th. We have nominations expected for the following categories of award that have been listed, those 6. If you have any inquiries, please reach out to the VP, and I'm sure that I will be able to shed more light on this after I finish. Next week by this time, the Port Harcourt chapter will be having their own technical presentation, and it will be a first at an hybrid attempt since COVID. So please register to join. I know that they plan to have both a physical and a virtual. Whichever one you're interested in, you still need to register to join. If you have inquiries, please reach out to Philip or the PS of the Port Harcourt chapter or the chapter coordinator himself. Their details are all as listed. The summer school that we announced earlier is now firmed. So 5th to the 6th of July, we have a 4-day summer school. We are discussing integrated formation evaluation of plastic reservoirs. And the intent is not really focused on fossil energy. We have opened this up to also take a lot of learning from the industry energy transition we are currently experiencing, and all the skill sets, the different aspects of geology that we know that will be getting this prepared for in terms of advancing their careers. So please join in. But the big news here is they are coming at a big discount for NAPE members. So if you're financially date as a NAPE member, either as an active, young professional, emeritus, and student member, you are getting a whopping 75% off your payments. Respectively, for members, it will be 20,000, and then for the student members, it is 5,000. If you are not a financially paying member or you are not up to date with your finances, then the full 100% payments would apply to you. As a snapshot, we have upcoming in July, the UK chapter technical meeting. You can see another summer school focused on petroleum economics. We have a couple of technical meetings also planned for July. But I'd also like you to please pen down the June 29th for a special, June 29th, yes, for a special technical webinar in celebration of one of our founding fathers. The details are being worked, but it will be announced very soon. We are planning to celebrate Chief Chambers Oyibo either the 29th or on the 30th as he clocks 80 he actually clocked 80 yesterday, but we would be doing this in honor on the 29th of June. We can't say this enough. We are vibrant on our social media spaces or our digital platform pages as listed. We ask that you please disregard the Twitter on it, okay? We ask that you please follow us on all the 3 platforms, LinkedIn, Facebook, and Instagram. And the address and signature is the same, is NAPE_Nigeria, if you are looking for us in that space. So that's it for me. Over to you, A.
Okay, thank you very much. I don't know if the briefing wants to throw some more light. If he does, yeah, you can go ahead. If not, we go ahead with our presentation.
No, no,
okay.
No, many thanks, Ehi. So nothing much to add, just to re-emphasize that the 30th of June is a deadline and is a hard deadline. So I think we still have enough time to respond and nominate any of our colleagues or yourself if you deem it fit to go for any of the awards that publicized. I think a mail went out some days ago, so please go through. But if you have any challenge, please write back to me and we're able to fix it at the committee level. Just to add.
Okay.
Many thanks.
Thank you very much. I once again want to say thank you to Dave, and I want to show appreciation for the Abuja chapter. I want us to say thank you to everyone who has attended this meeting. The president will be telling us the closing up and giving us a special thanks at the end of the meeting. But before we do that, I want to appreciate Dr. Dave. We want to present to you a certificate, so Ayo can go ahead and present and show it while Dr. Ajayi presents it to you.
Thank you very much. On behalf of NAPE Abuja, we'd like to appreciate you, Dr. Dave, for coming and for the most outstanding presentation. And we'd like to present this token to you. And we hope when we invite you next time, you're going to honor our invitation. Thank you so much. God bless you.
Thank you. Yeah, no, I appreciate that. That's lovely. Thanks.
President, you're on.
Please allow me to share my video.
Okay. Tunde.
Okay. Can you try and share it now, ma?
It's still saying no. Post has stopped it. Well, okay. I'll go ahead without the video.
Okay, so, share it now. Share it now.
Yeah, Dr. Dave, you did not disappoint. Thank you so much for bringing us back to the basics. I am extremely delighted that I brought my learning cap today. And you showed us that we really need to go back to the basics, look at things like the Allen fault maps, the juxtaposition, what is in the fault gauge material, because they actually make or break our prospects. And I particularly love the example where we could triple or quadruple the gross rock volume just from a proper understanding of what your faults are doing. So for every geoscientist on the call, please, the key takeaway is to pay attention to those faults and see what they are doing through geological time. Thank you so very much, Dave. That was a very enjoyable, extremely educative talk. I look forward to when we can have you for a bigger audience. And to the Abuja chapter, thank you. This is a fantastic job of pulling. At a point, I counted almost 90 people on the call. That is fantastic. And so for everyone who is not yet a member of NAPE, or who is in the Abuja area and is not a member of Abuja chapter, please try to link up because there are benefits. As the publicity secretary just stated a few minutes ago, you saw that there's a whopping 75% discount on things that are going to benefit your career into the future. I mean, we all are in this for the long haul. I would encourage everyone not to listen to the chatter about what is going on in the marketplace. We've been this way before. It's a cyclical thing, so please be encouraged. And while we're in the doldrums, let's learn as much as we can. Thank you all and have a fantastic day. Great job, everyone. I'm really proud of you all. Bye.
Thank you very much, Ma. Well, before we close the meeting, I found that the president-elect, who is in charge of the educational aspects of this of NAPE. Dr. James Edet is around. I don't know if you can just say a word or two before we close the meeting. Dr. James Edet, please.
Right. Thank you very much, Heave, for asking me to say a few words. First of all, let me say, Dave, this is something I have always thought about, and I am happy to make us realize. Because every time I saw those maps and I saw those huge black gaps, I always wondered, what's going on here? And I could never understand it. Thank you for bringing it all back to us. As the president has said, it's time to go back to basics. And chapter for putting all this together. This must be one of the most thrilling webinars I have attended. In fact, I got so focused and I thought I was going to sort of like find it the usual boring talk, but this was far from it. Very educative, very incisive, and Dave, thank you very much. This is good. And to all that have been part of this, I say a very big thank you and hope you are getting a lot of mileage from your membership as NAPE members, and we hope to continue to give you all the best. Thank you very much. Ehi, back to you.
Okay, thank you very much, Dr. James. Dave, thanks again, once again, and we hope to see you again soon, and learn a little bit more from you. On behalf of the chapter, we say thank you, and we'll be closing the meeting now. Thank you very much.
Yeah, thanks to everyone on the committee and the invite. Great talk. Thank you all for your organization and your hospitality.
Thank you.
Thank you very much.